Okay, as Lee said, my name is Dan Fanbro, and my specialty is highway and traffic engineering, and that's the topics that I'll be talking about tonight. Basically, what I'm going to do is take section 16 in your reference guide, and we have basically the notes that I sent over taken pretty much in order of section 16 in your reference book. I've tried to maintain the same numbering in my notes as the sections are numbered in your book, and so this is just an idea of the topics that we're going to talk about. And there's 32 of them in your reference guide. You'll notice that we'll use problems. We'll supplement these with some other problems from time to time, and there's some additional material in your notes that aren't in your reference guide. So we'll talk about these topics, but before I do that, let me just say, as a reference guide, something that I found was pretty good and you might want to take a look at is this book by Lindbergh. It's the quick reference cards, and in it is a set of equations for the traffic part of the session. It's on page 36 if you had this particular book, but it has all of the equations that you'll need for the traffic part of the exam. And over in the surveying section, which is the following two sections, the following section, it has about horizontal and vertical curve layout, which we'll cover tonight as well in highway design. The one thing that's missing from this reference guide are the equations for pavement design, and that's because of the length of them that they'd have to deal with just wouldn't fit nicely in this particular book. The advantage is that your reference guide has a pretty good set of nomographs, tables, and procedures on the different methods of designing pavements. Okay. What I'd like to start with is section 1 in your reference guide. It's called Definitions and Acronyms. And we're not going to go through all of those things that are listed in the guide, but I would like to bring your attention to three things that I think are important, just so that you know what we're talking about there on the in acronyms. You'll find that transportation engineers, I don't know whether it's worse than other type of engineers, but we like to use acronyms. And I think that we invent these things so that no one else will understand what it is that we're talking about, and they'll think that we're smarter than we really are. But three acronyms that are important to you in this particular review session are AASHTO, which is an acronym for the American Association of State Highway and Transportation Officials. Now, you don't really need to write that down. I just want to tell you what it is. But that's an organization that's made up of representatives from the state departments of transportation, and they have committees that get together and they establish design policies on a national level, and they publish documents which the different states pick up and they develop their own standards from. You'll find several places in your notes reference to AASHTO policies, and this is an example of one of the things that's referenced in your text in terms of design guidelines for highways. It's called AASHTO's Policy on Geometric Design for Streets and Highways. And it's got all of the standards that state DOTs use are in this book. It's not a good reference book for an exam because it's all text and there's very few examples of how to do things. But they do use some tables in some of the examples in your reference guide. AASHTO likes to refer to their publications by the color of the cover. So highway engineers will typically call this the Green Book. And everyone in the profession knows that. Everyone not in the profession has no idea about what it is. But AASHTO is a very important player in the design of highways especially. Geometric design and pavement design, both of which we'll talk about. You'll also find reference in your manual to a publication, to an acronym called HCM, or the Highway Capacity Manual. A different national organization, the Transportation Research Board, puts together this document, but this is sort of the Bible for traffic engineers on how to do analysis of intersections, freeways, two-lane highways, etc. And we'll talk about capacity and level of service tonight, and they'll refer to this particular document. Again, this is not a good reference to have for the exam, but it is something to know about. What would I recommend as references if you were looking for something to take to the exam? I mentioned the quick reference cards that have the formulas. If you had access to a transportation engineering textbook, I happened to pick one up out of my office. Not that this is the best one, but what you really need to watch out for if you pick up a reference to take in is something that is 1985 or later. If you have something that's older than 1985, it will have procedures that will be out of date, and they're going to be working examples that are 1985 and later technology. So any book on transportation engineering, textbook, as long as it's newer than 1985, would be a good one to have. Another good source of material, there are some handbooks. This particular one is by the Institute of Transportation Engineers. It's called Traffic Engineering Handbook. It'll be good for traffic, but not so much for the pavement design. And I'm not sure, but this does have some good information in it that might be of use to you. Now, with all of that said, let's move. The one other acronym that I put down there is CBD on your notes. That's not really a textbook or an organization, but it's something that I'll probably use a couple of times tonight in the lecture. And that's an acronym for Central Business District. In most of the urban areas, the downtown area, where all the skyscrapers are and the concentration of business, is called the CBD. And we tend to use that term quite a bit in talking about traffic analysis, and no one seems to know what we're talking about when we use that term. If I move to slide number 2, we're talking about vehicle dynamics, and in your notes, if you look at that section on vehicle dynamics, what we're really looking at is using Newton's second law of motion to describe the way that vehicles accelerate, decelerate, skid along pavements in accident reconstruction or analysis, and a number of things that we do in transportation engineering analysis. And it goes back to the old formula that F, or the force, normal force, is equal to the mass times the acceleration. And we can define mass as the item's weight divided by the force of gravity there. We can look at net tractive force, which I probably should have some drawings here, but the normal force minus the weight of the vehicle. The normal force is equal to the weight of the vehicle minus the friction force of that particular vehicle. And we can look at this net force and the horsepower formula you see on the bottom of that particular slide. Now, when we use Newton's second law of motion, we're going to be looking at the relationship between the vehicle's position. We're typically talking about vehicles here, the vehicle's velocity and the vehicle's acceleration. We're really looking at a linear motion or a uniform acceleration as a function of time. And there's a series of equations there in your reference guide. There's also a very good series of equations in these quick notes that I was talking about. It basically says that acceleration is a function of is velocity divided by time. Velocity is distance divided by time, and the distance is a function of the velocity, or a function of the acceleration over time squared there. And we can use those particular relationships, and generally if we know two of the three relationships, we can solve for the other, or missing the missing variable in that case. If we take some examples, and these examples come from your, this particular one comes from your notes, we might have a 4,000-pound car that's traveling at 80 miles per hour and skids 580 feet before stopping. And taking those equations, we can calculate the time that it would require for that vehicle to come to a stop. The first thing that we'd have to do is to compute the vehicle's initial velocity. And in working with these equations, the biggest mistake that people make is the unit conversion problem, because invariably the speeds that vehicles are traveling are given in miles per hour, and these equations are all written in terms of feet per second. So we've got to be able to get a common set of units here. So in computing the initial velocity of 80 miles per hour, the first thing we have to do is to convert that to an equivalent number of feet per second. And we do that there in calculating the initial velocity of 117.3 feet per second. And then we know that the distance that vehicle takes to stop was given to us as 580 feet, and we know that the final velocity at stopping is equal to 0 feet per second. And then we can take the time is equal to 2 times the distance divided by v sub o, and that should be minus v there in the denominator of that particular equation, and it'll carry over into the numbers as well. So we'd simply substitute the numbers in, and we would compute that it would take 9.89 seconds for that vehicle to skid to a stop from 80 miles per hour. Okay. You might note that in that particular problem, we didn't have to use the 4,000-pound weight to come up with part A there. Okay. If we look at the vehicle's acceleration, and I'll use acceleration there because it's what we're talking about. Acceleration is equal to the final velocity minus the initial velocity divided by the time that was required for that vehicle to come to a stop. And again, I'm missing a minus sign. It should be 0 minus 117, and you'll note that it should be minus 11.9 feet per second squared there in that particular problem. The negative sign really means that the vehicle is decelerating to a stop, but we generally talk about acceleration. If it's positive, the speed is increasing. If it's negative, the speed is decreasing. So a negative acceleration would be the same as talking about deceleration in this particular case. We can look at the retarding force on the vehicle there. If we know what the mass of the vehicle is, which is simply taking its weight divided by the acceleration of gravity, 32.2 feet per second squared, multiplying that by the acceleration, in this case the minus 11.9 feet per second squared, what we come up with is a retarding force of 1,480 pounds of force. And we can use that retarding force to calculate the coefficient of friction. And this is really the force as that tire is skidding along the pavement. This is the force that's acting parallel to the pavement surface and causing that vehicle to decelerate to a stop. And that's simply the retarding force or pounds of force divided by the normal force of the weight of that vehicle acting straight down on the pavement. And that ratio is 0.37. Okay. Just to give you some reference there of what a 0.37 would be indicative of, that's probably a wet pavement surface to get a friction coefficient that low. I don't think in your reference book they give you tables for typical friction values for different surfaces. I have seen some reference books that do it, but generally for dry pavements you're talking about friction values in the 0.7 to 0.9 range, and for wet pavements you're talking friction values in the 0.3 to 0.5 range. So if you get into a situation where you have to assume a friction value, those would be some values to look at there. Okay. So really it's pretty straightforward, using things that concepts that were first introduced in physics to go through it. Now let's look at a problem that is a little more complicated but uses the same basic principles. And this is an example problem that we have, and I'll try and point out what the important things are in this particular example. We have two cars that are traveling at 60 miles per hour, and those two vehicles are both in the same lane, they're traveling in the same direction, and they're initially 200 feet apart on a level roadway. The leading car hits a disabled milk truck and comes to an instantaneous stop. Okay. And we're making some assumptions here in this particular problem. And the driver of the trailing car, whose perception and reaction time, and that's really how long it takes the person to become aware that the vehicle in front of them is stopped in their lane, take their foot off the accelerator and put it on the brake, but their perception reaction time is 0.5 seconds. And that's really the lag time before they actually start stopping. Once they step on the brakes lock and the vehicle skids into the lead car. And the coefficient of friction between the roadway and the skidding tire is 0.6. So that's really the situation and the givens of this particular problem. This is the type of problem you might encounter on the exam. And sort of the way that it might go is they might first ask you, how far does the trailing car skid after the brakes lock? Well, again, the first thing you have to do is to convert the car speeds to some common units, convert it to feet per second. If you know they're traveling at 60 miles per hour, simply converting that to feet per second, that comes up to 88 feet per second. And then you have the distance the trailing car has traveled by the time its driver perceived the danger and applied the brakes. Remember I said the given situation was there was a half-second perception reaction time, which means that the trailing vehicle traveled, in this case, 44 feet before they ever stepped on the brakes in the first place. So they started out 200 feet apart. Now they're only 200 minus 44 feet apart before actual stopping takes place. The total skidding distance is showing there as, I believe it says it says the total skidding distance is 120 feet minus this S1, which was 44. And if I look at that problem, there must have been a typo on that first given. So why don't we go back and make the correction on page
Situation 101,
yeah.
Second line. So your two cars were actually 120 feet apart,
right? Yeah.
Before this
Yeah.
guy ran the milk driver down.
Yeah. If you go back to where it says situation 101, it says the two vehicles are 200 feet apart. It should say 120 feet apart. Okay, and then the givens will match the solutions here. Now what that means is they started out 120 feet apart. The second vehicle traveled 44 feet before they began to stop, and then it skidded until it hit that milk truck, so the total distance that it skidded was 76 feet. Okay. Now we're doing all of this to answer how far does the trailing car skid after the brakes lock, and that would be 76 feet, or the answer there at the bottom of that particular page. The second follow-on question here is, what is the speed of the trailing car at the moment that it collides with the stationary lead car? This is the car that hit the...
Okay, we're in good shape. Now he does his magic.
Okay.
I recognize the shiny head.
Which one?
There's 3 of us.
Now, Anel, if you fall asleep again, you have to be careful not to fall on that off switch.
Are you drinking over there?
I'll remember that.
Okay.
Yeah, you got a lot of distortion in your picture. I don't know if it makes any difference. We just thought you guys were drinking, or maybe we were drinking.
It should clear up in a minute or two.
All right. Seems like your end always clears up a lot.
There you go.
A lot quicker than ours does.
You're cleared up now.
All right. Dan?
Okay, I think
Well, we lost. I was going to say we lost you just when you were talking about Newton's second law to find the deceleration of the trailing car during the skid.
Okay, let's go back to that overhead, and we made a few marks on it while y'all were gone.
Okay.
When we're looking at, and part of the problem is my word processor didn't print out all of the mathematical symbols in this, so I want to make sure that we get them right as we go through these notes. The frictional force on the trailing car depends on the coefficient of friction and the normal force, which is equal to the car's weight. And it's going to be negative because it opposes the existing motion. So this friction force that we have is equal to minus F times the normal force, which is really equal to minus the friction force times the weight of the vehicle. And that negative 0.6 was given to us in the description of this particular problem as the coefficient of friction of the pavement surface. And the weight of the vehicle would be equal to its mass times the acceleration of gravity. So we can then use Newton's second law to find the deceleration of the trailing car during the skid. When we look at that, we have that friction force, or the negative 0.6 times mg divided by m, or the vehicle's mass. So really now we have, and that should be a negative 0.6 times mg divided by m. So the mass cancels out, and we're left with again negative 0.6 times 32.2 feet per second squared, or a deceleration of minus 19.32 feet per second squared. So I'll put another negative sign in there as well.
In front of the 19?
In front of the 19, I'll put a negative sign. We can then use the uniform acceleration theory to compute the velocity of the car at the moment of impact. We know it started out at 88 feet per second. It skidded, it was decelerating at minus 19.32 feet per second during the skid. We want to find out the speed at the point of impact. And we would go back and use an equation looking something like this. Back on the next page, this v, or the velocity at the point of impact, would be equal to the initial velocity squared plus 2 times the acceleration times the distance over which that travel took place. And again, note I put the plus signs underneath the radical there. Initial speed was 88 feet per second squared plus 2 times the acceleration. It'll be a negative 19.32 in that case. and that's multiplied by 76 feet, or the distance over which skidding took place. And if my math is correct, you come out with a velocity of 69.3 feet per second at the instant that impact is made with that car that just ran into the milk truck in front of you. Okay, again, just a caution, note that all of those velocities are shown as feet per second, including our answer there. Okay. So now we know the speed at the point of impact. Another question that might be asked in this particular problem is that if the trailing car is able to skid past or not into that stationary lead car, there's nothing in front of it and it's just skidding to a stop, what length of skid marks would it leave? In the uniform acceleration theory would predict the skid distance as skid distance S is equal to the final velocity minus the initial velocity, those two squared, divided by 2 times the acceleration. So again, if I go back to your notes there, we need to put a couple of negative signs, one minus sign and one negative sign, in that formula, and we would come up with a skidding distance of 200 feet if the vehicle simply skidded to a stop once the brakes were applied on a pavement whose friction was 0.6. And this is actually the way accident reconstructionists, police officers, or whatever, they compute speeds of vehicles that are involved in accidents. They can go out and measure the skid marks left on the pavement and come up with some estimate of what the initial speed was, knowing something about the pavement surface on which that accident occurred. So this just sort of walks you through one typical example of how you might use these equations to answer a series of questions about vehicles skidding on a pavement surface. You could have similar type questions for acceleration, and we'll talk a little bit more about those in some of the design situations a little bit later this evening. Section 3 in your reference book is titled Banking or Acceleration, and when you look at that, banking or superelevation, terms that we use to describe when you have a curve on the roadway. What you'll notice when you're driving is that it's banked, and it's banked to try and keep vehicle, when you're traveling around a curvilinear path, there's a force that's acting on you that's trying to throw your vehicle off of the roadway, pushing you out and away. And we use the banking of the roadway to counteract that force. And you'll see some pictures there on the bottom of your notes to sort of explain what we're talking about. Vehicles are traveling into the board or into the paper there, making a curved or going to be on a turning path to the left, and there's a force that's acting, pushing the vehicle out as it travels around this path. There is a normal force that's acting down, holds the vehicle on the roadway surface, and there's also a friction factor, the pavement's friction, that also helps to hold the vehicle on the roadway. And we can use the equation at the top of that page to compute what the radius of that curve needs to be for certain speeds. And in that particular equation, it's E plus F is equal to the vehicle's speed divided by 15R. And you'll note in this particular equation, the velocity is given in miles per hour, and that's because the conversion has already been made, and that's where the 15 comes into play at the bottom there. The E in that equation is the rate of banking, or the rate of superelevation on that curve. It's generally given in units such as 0.06, 0.08, or 0.1, and that's how many feet of rise per foot of run banking we have on that curve. And you can see E given on the bottom figure of the figure there. For 1 foot of horizontal distance, how many feet of rise? Typical values I mentioned are in the neighborhood of 0.08 to 0.12. We have the plus the F, the friction factor, because I mentioned the banking and the friction work together to keep the vehicle on the roadway. And friction values mentioned a while ago for dry pavements are in the 0.7 to 0.9 range. Wet pavements are 0.3 to 0.5. Although typically we design for much lower friction values than what the pavement will provide. There's a factor of safety built in, almost a factor of safety of 3 in horizontal curve design. And that's why you've all been out driving on the highway. You see those advisory signs on horizontal curves. You can always drive faster than those signs say, and that's because of this factor of safety that's built in to our horizontal curve design. Typical values for building or designing roadways are in the 0.2 range for friction values. So the pavement will provide much more than we're using in design. And typically what roadway designers do is they know what superelevation rate their particular state or DOT uses. They know what the design friction values are. They know what speed they want people to operate on, and they'll substitute to come up with what radius they need for a particular horizontal curve based on design guidelines. So that's how this or superelevation comes in. We'll come back to this in a few minutes talking about horizontal curve design, where we compute some radiuses, but this is a very useful equation right here for computing radius. The one thing, again, let me just caution you about this particular equation. Generally when you use it, you'll come up with if you work backwards and compute a velocity or a speed, that's not the maximum speed a vehicle can go around the curve. That's really the design speed, which again has a factor of safety built into it.
A couple of questions on that.
Yes.
Just wondering if we see on the test. First of all, with the interstate and the federal standards, what do they usually design for as far as velocity?
We're going to talk about that in a few minutes on one of the later slides. Let me just briefly answer it now and then come back to it. But most of the interstate designs are done for speeds of 70 miles per hour at present, which is slightly higher than the speed limits on those roadways, but that's generally the philosophy that most of them follow. You'll find in some of your older urban areas that you'll have some sections of freeway designed for 50 or 60 miles per hour, and generally when you have a section like that, there'll be signs, warning signs, alerting you to what the supposed safe speed is on those roadways. But I'll explain in a few minutes how we go about deciding that.
Okay. The other quick question was, will we see any metrics on the test? Are they likely to use kilometers per hour or meters? Do we have those conversions also?
I don't think you're going to see any metric in terms of highway design on this exam. I don't think. And the reason for that is that the metric standards were published in January of this year. And I don't think they've had time to update the questions for this spring's exam.
One thing I think you can always do is you just flat crush everything back into units you're familiar with, and when you get the answer, you crunch them back into metric and you mark a little box.
That's a way of going about it, but my guess would be no metrics in highway design because it simply hasn't been out long enough to get example problems in metric. Okay, but that is a good question. I suspect that the next exam there will be metric questions on highway design in the fall of the year. Okay. Let me move to section 4 and talk about sight and stopping distances. A very important concept in highway design is something that we call sight distance, and there's a whole host of different sight distances that are important to us in highway design. Basically, when we talk about sight distance, we're talking about the length of the roadway that the driver is able to see. And what we typically design for are things called stopping sight distance, passing sight distance, decision sight distance. Not all of those are shown on here. We really only have stopping sight distance because that's really the controlling one that we have to provide. And stopping sight distance is some distance that the driver has to be able to see that will allow a driver that is traveling at the maximum or the design speed to stop before coming upon an observed object. Now, this particular formulation or model has been around since the 1940s, hasn't really changed all that much. But what we're really trying to design for is to make sure that the driver can see far enough ahead that if there's an unexpected object in the roadway in front of them, that they will be able to bring their vehicle safely to a stop. Now, the basic model is shown there in the middle of the page, the stopping sight distance equation or the stopping sight distance model. It is a byproduct of AASHTO or the state DOTs. Now, there's if you look at that particular formulation there in the middle of the page, it says the stopping distance has two components in it. There's the 1.47 times T sub P times the velocity, and that's the perception reaction distance. The T sub P is the time it takes the driver to recognize the hazard, take their foot off the accelerator, and put it on the brake. The velocity, or V, is the speed in miles per hour that they're traveling along the roadway, and that 1.47 is nothing more than a conversion to convert miles per hour to feet per second, getting it back into units. So that's the time the vehicle actually travels before stopping or before braking begins. The second part of that equation is the distance traveled once braking begins till the vehicle skids to a stop. And that is the velocity in miles per hour divided by 30 times F, or the friction factor of the pavement, and that should be plus or minus G, depending on whether they're going uphill or downhill, will help the friction factor there. Okay. F is the friction factor. We just talked about that in vehicle dynamics, that V squared over 30, there's the conversion from miles per hour to feet per second, and so that is a miles per hour in the top, and that 30 is a result of that conversion on the acceleration of gravity. Friction factors, they're going to be decimals, 0.3 to 0.6 in that range, maybe up to 0.9 for dry pavements. And then G is the grade, and it's grade in a decimal. So when we talk about a 2% upgrade, that would be entered into the equation as 0.02, or a 4% upgrade would be 0.04 in that particular equation. And
upgrades get the plus number.
Upgrades get the plus number, and downgrades get the negative number. because if you're on a grade, that will help you. You have the gravity helping you stop sooner, or gravity making you stop in longer distance, depending on whether you're going uphill or downhill. Okay, and we simply substitute into that formula for different speeds we want to design for. And let's take the interstate example that we talked about a few minutes ago. If we wanted to design a roadway for 70 miles per hour, we would simply substitute 70 into that equation, and if we knew there's a friction value in a table for 70 miles per hour, and for level surface, we would use a perception reaction time. We could compute what was the minimum stopping sight distance we have to provide at every point along that roadway, and then that would control how sharp our horizontal curves could be, or how sharp our vertical curves along that particular roadway could be. Okay. Let me just briefly tell you about some of the assumptions in that particular model. The T sub P, or the perception reaction time for design of most highway facilities, is 2.5 seconds. And the rationale behind that is that most people could perceive and react to an object in the roadway in less than or equal to 2.5 seconds. We typically use 85th percentile values rather than average values for things that we use in design. So we don't design for the average driver, but we pick values that almost all drivers are able to accommodate. You'll note in the line just above that it says that when we're designing roadways and stopping sight distance, we have to know how high the driver's eye is above the pavement surface, and that height is assumed to be 3.5 feet. Again, that's 85% of the drivers are at that level or above, and the object height that's being used is an object that is 6 inches tall.
Was that armadillo?
It's actually something slightly smaller than an armadillo, more like a small jackrabbit or something like that in the road. But it is a small, unexpected object. And just one sidelight to that: when we're designing, not only do we use these 85th percentile values, which are conservative in itself, the other assumptions that are in that model is we're going to design for a wet weather or wet pavement friction for a person that has bald tires in a locked wheel stop. So again, there's a large factor of safety that's built into these particular equations. Now, if I could move to section 5 in your notes, we're going to talk about designing circular curves and horizontal curves, and some of the equations that we can use to come up with a set of field notes or design values for these curves. You may see these things repeated in the surveying, because that's really where the basic circular curve and vertical curve layouts come from. But we'll go through them tonight, talk about some examples, and you may get a little bit more on this in the surveying section. This particular slide is not in your reference book, but it is included in the little quick reference guide that I pointed out early on in the evening. But basically, if you look at this particular drawing, you might think of your roadway starting here, sort of running from where my pen is on this overhead, lower left, and heading in the upper right direction. We typically have tangent sections of roadway, and that's what the T would represent in this particular diagram. You might also pay attention to the following page. Has a lot of these acronyms defined, but I want to talk about them just a minute. We have our tangents, which are designated as T, and you'll notice a couple of points on that curve: PC, PI, and the PT. I'll talk about PI first. Is the point of intersection where those two tangents intersect, and the PC is the point of curvature where you go from a tangent section to a curved section. The PT is the point of tangency where you stop the curved section and go back to the tangent section. So we have, again, the PI, the PC, and the PT. And generally, what you see the PC, this is the way we would be designing or laying out this particular piece of roadway there. Probably the next most important part there is I, which is sort of in the top of that particular drawing, and that's the angle of intersection of those two tangents up there. You'll also see it referred to as delta in some surveying textbooks. More commonly, though, I think you'll see it referred to as I. Now, in highway design, there's a couple of different ways to do it. Most of your textbooks, though, will use something that's called a chord definition. And you'll note in this particular drawing there is a 100-foot, I should say arc, I said chord, it's a 100-foot arc that's drawn out there, and that's really a distance of 100 feet along the arc of that particular horizontal curve. And down towards the bottom of the drawing you'll notice something that's called D, which we refer to as the degree of curvature. And typically what we will do is that for a certain speed we know that we use we'll look up in a table a degree of curve that we can use for that speed. And that degree of curve is defined as really what degree of curve for that 100-foot distance of circular arc that we have there in the top of that particular drawing. So we have these definitions, the arc definition, there's a chord definition, but the more common is the chord definition there. Okay, so we've got degree of curve. You'll also notice radius for that particular curve. And we'll work a problem in just a minute where we look at some of those things. Now the following page in your notes is sort of the definitions of the things that were on that particular drawing. You can go one page over and begin to find your horizontal curve equations. And you'll note on those horizontal curve equations we have, if you go back to geometry, you can see your radius is equal to your long chord, and that's the distance around that chord from the point of curvature to the point of tangency, divided by 2 times the sine of the angle of I over 2. And you can come up with tangent lengths and a whole host of different things about that particular curve based strictly on going back to geometry. So I think all of those things are explained in that particular, if you look at the drawing and the definition and these particular equations. Now there are a couple of things that are probably important from highway design, and that's over on the far right of that particular chart where it says D equals 5,729.58 over R, and that's if you know what the radius of the curve is, or if you know what the degree of the curve is from your design tables. If you know what the degree of curve is, then you can compute the radius that you would need for a particular curve. And that one would be important if you're designing highways. If I look at the example, which is one page over, and we're going back to the larger font, something that you might be given as a part of a problem is your intersecting angle between the two tangents is 35 degrees. The radius of the curve is 1,000 feet in length, and the station of the PI is equal to 50 plus 0, 0. Surveying or highway design, we talk about stationing. That's would be 50 plus 0, 0. If we were writing that out, that would be 5,000 feet from the start of the job. Those 0, 0 are the two digits in the hundreds there. If we wanted to go out and be able to stake out that particular curve, a set of calculations that we would have to go through is to compute what half of the intersecting angle would be is 17.5 degrees. The degree of the curve we're computing in this case. It's not really a design problem because we didn't look up degree of curve from a design table, but we could compute the degree of curve as that 5,729 divided by the radius, which was 1,000 feet in this case. So we'd have a 5.7 degree of curvature. I know from highway design that that's a pretty sharp horizontal curve, and people would have to slow down in order to get around it pretty well. We can compute the length of the tangent, or the tangent length here is equal to the radius times the tangent of 17, and that should be 17.5 degrees there rather than 17.7. And I think the numbers there are equal to 315.3. Okay. Now, when we look at the length of the curve, okay, and let me talk about tangent though before I get away from it. If you go back to your drawing of your circular curve length and look at that, let me explain to you what we're doing. We've got our stationing or our reference points laid out along those tangent pathways there, and we know that the reference point for that PI is what we call station 50 plus 0, 0. Okay, but you'll note that that station is not going to be on our roadway alignment. It's up above it there. So when we compute this tangent length, 315.3 feet, what we would have to do is to measure back from the PI, or take that 50 plus 0, 0 and subtract, in this case it would be 3 plus 15.3, and that would define where our point of curvature was starting. Okay, so we're working back from that PI. So now we know where along that alignment our curve starts, and we compute the length of the curve using the next equation there. It's 100-foot stations divided by 35 degree angle divided by the degree of curvature of 5.7, and it tells us that our curve is 610.8 feet in length. Okay, so now we know what the station is, or the reference point for our point of curvature, 50 minus the 3 plus 15, and if we then take that reference point and add to it the length of that horizontal curve, we know what the station is where our point of tangency begins again. Okay. You'll probably also recognize that it's going to be a shorter distance to get around the circular curve on that circular path than it would be to take the two straight lines or the two tangents that were there originally. Common mistake that people make in working these types of problems, it's very easy to trip someone up by asking them to calculate the PT station. And the tendency is to calculate the tangent length and simply add that to the point of intersection, reference point. And when they do that, they haven't taken into account the gain in distance they get by traveling along that circular path. So you've got to work backwards, then compute the length of the curve to go all the way over there. Okay. Now, when you look at these, the calculations that follow along there, if we were actually laying this curve out on the roadway, these first stations that we're looking at there, remember we're starting at our PC at what was called station 46 plus 84.7. And we would like to get to some even stations there. First one would be 47, and that's only 15.3 feet away from the point of curvature. The first deflection angle that we would have to turn in order to get to that point would be 26 minutes, 19.8 seconds, and the first chord distance to measure would be 15.3 feet. Essentially that would mean, and again this is going back to surveying, we would go to our PC, sight along the tangent there. We would turn an angle of 26 minutes, 19.8 seconds, measure a chord of 15.3, and that would be the first point along that particular circular curve. Okay. Once we have that point, then we can compute our full sections, or our 100-foot chords for the bulk of the curve, and each of those would be a deflection angle of 2 degrees, 51 minutes, 53 seconds, and the chord length that we would measure to get to that 100-foot arc would be 99.96 feet. So we would turn, we're at 47, then we would go to 48, 49, 50, 51, and so on until we got out to the end of our curve, and that last one that we would have to measure to go from 52 plus 9.5 up to, well, from 52 to 52 plus 9.5 would only be an arc of 95 feet. And to get to there would take a deflection angle of 2 degrees and 44 minutes, 16 seconds. And that last chord that we would measure would be 95.52 feet.
Where did that .3 come from, Dan?
This .3, I think, is it's a correction factor to get to it there. That is a good point. There is a .3 in those equations for this last deflection angle, and
It actually appears on every one of them.
yeah, it is a correction factor, I think, to get it to minutes and degrees there. And then just to give you a picture of what that would look like, there's the following page there that talks about vertical curve layout by deflection angle methods. If I could get the overhead there in your notes. This is just simply the calculations for that particular problem, illustrating the process that we just went through. And you'll notice there in that slide, down in the bottom, you see these degrees of curvature, and those are the angles that are subtended by a 100-foot arc in this particular definition. Okay. So really, the only change that you would do for a design problem is that design problems typically give you the speed you want the roadway designed at, and you go to a table and look up what degree of curve you can use for that particular speed. Okay. Let's talk about vertical curves, because that's the other types of curves that we design for. And when we look at crest vertical curves and sag vertical curves, let me just say that a crest vertical curve would be one that was going over the top of a hill, and a sag vertical curve would be one that was going through a valley. So that's the two that we're looking at there. There are a couple of different types of crest and sag curves. I don't think they're real. I don't think they're real important. I just wanted to draw a couple of curves here on that on this for you to illustrate crest and sag vertical curves. What do we use for design controls? Well, you'll notice that for crest vertical curves, we use stopping sight distance. We'd like the drivers to be able to see far enough over the crest of that hill to stop if there's an object in the roadway. And it's a 6-inch object that we're trying to provide them sight distance for. So stopping sight distance is one control that we look at. Now the second criteria that we use is rider comfort. The length of the curve has to be equal to something that we call A, or the algebraic difference in grades. That's defined on the next page, but divided by 46.5, and that's just an empirically derived constant there. But where we use this is getting into very short vertical curves, maybe the driver can see over the top of, but we don't want to create a bump in the road that would be uncomfortable to that driver. So there's a minimum length that's based on rider comfort. Now, if you look at sag vertical curves, the first thought that comes to mind is, well, we really don't need to see for stopping sight distance because there's nothing there to block the driver's view of the roadway. But at night, we would be looking at, if there's something in the roadway, it has to be picked up by the headlights of the vehicle, so it's the headlight beam distance that defines the length of our sag vertical curves. And it's a nighttime problem that we're looking at. We also have concerns about rider comfort. And we'd like to design our highways long enough vertical curves that it's not like riding roller coasters at the amusement parks. And you've probably all been over a curve that's like that. The other thing that comes into play is drainage requirements, especially at sag vertical curves, that you want it to have enough slope on it so that water doesn't pond at the bottom of the hill and basically create a drainage problem that the vehicles might hit and go out of control. And then we also give some thought to the general appearance of the roadway and certain criteria we have to meet so that it looks good to the driver. So those are some of the things that we consider. And the equations that we would use to design those curves are shown on the next page in your notes. And really that's looking at, there's two things there. It says stopping sight distance. And we have two cases where the sight distance is less than the length of the curve or the sight distance is greater than the length of the curve. And that's what the S and the L are, sight distance and lengths of the curve. We also have the equations there. The length is equal to A, this algebraic difference in grades, times the sight distance squared divided by 100 times the summation of these the square roots of 2h1 plus 2h2, and that quantity squared. Now, h1 and h2 are the two heights that we talked about a few minutes earlier. The height of the driver's eye above the pavement surface and the height of the object that the driver must be able to see there. And those two values were 3.5 feet for the driver's eye and 6 inches or 0.5 feet for the object that the driver has to see. Okay. Now, I think what I would like to do on this particular slide is to illustrate what A is. If we look at two grades here, a +2 grade that's intersecting a -3% grade, we talk about this algebraic difference in grades. It's the absolute value of the difference in those two grades. So when we have a +2 minus the -3 grade there, we would compute an A of 5 for this particular set of conditions. Now, what would happen had it been a -2 intersecting a +3% grade? The algebraic difference in grades is still going to be 5. Okay, so it's this absolute value of the difference in those two grades there. So when we talk about A, we're talking about, in this particular example, a value of 5.
The units H have to be feet.
The units H would have to be feet in this particular equation. That's because that sight distance is normally given to you in feet in this particular formula. Now, it becomes a little more, I think, clear when you start looking at the drawing on the next page of the vertical curve formulas. We have a roadway again that's going from left to right in this particular example, and you'll note that we have something called G1 and G2, which are really the grades of that particular roadway. It's going to be a crest curve because it's going over the top of a hill in this particular case. You'll note that we have tangents. Back tangent would be back from the point of intersection. The forward tangent would be forward from the point of intersection. We have our PVI, or the point of vertical intersection. We had a PI for a horizontal curve. We have a PVI for a vertical curve there. And you'll notice sort of at the top of that particular drawing there's an L, or the length of the horizontal curve, the length of the vertical curve in this particular problem. We also show chords there, which aren't really that important to vertical curve design. What is important is something that we're calling Y in this particular drawing, or the tangent offset, because we typically can compute what the elevation of that tangent line is, and if we can compute this offset, then we know where the elevation of the roadway surface is going to be. So typically we know the elevation of the tangent, we compute Y. In this case we would subtract Y from the elevation of the tangent to compute the elevation of the roadway surface. Okay. So there are a series of vertical curve formulas on the next page that sort of define all of the variables that were used on that particular drawing. And I think they're pretty much all there. A couple of things to point out. We talk about X as being the horizontal distance from the point of vertical curvature to a point on the curve, and X sub m is the horizontal distance from the minimum to the minimum or maximum elevation on the curve. Now, if I go back to the drawing, just point out a couple of things there. We're talking about these horizontal distances from the PVC, that's where the vertical curve starts, to some point on the curve. This horizontal distance would be along a line here horizontally from the PVC. Okay. X sub m is where the minimum or maximum elevation point is along that particular curve. And we can compute where that value is. Now, important point when you're looking at minimum and maximum elevations, the natural tendency is to think that for a curve of this type, the minimum or maximum point is going to be halfway between the two ends. And that's not always the case. That's only true when you have a +2 intersecting a -2, or the plus and the minus grades are exactly the same. If they're different from one another, then that minimum or maximum point will be closer to one side than it is to the other. It's not the middle of the curve. And then we look at these particular, the formulas there for vertical curves. And again, we'll work a couple of problems on vertical curves because I can almost guarantee that there will be a vertical curve formula on the exam that you take. There always is. Sometimes there's more than one vertical curve equation. Very popular types of problems for exams.
Very easy to grade, very little interpretation.
Yeah. So let's look at a couple of examples, if you will. The first example, and there's some good parts about this example, and there's some not so good parts about this example, and I'll try and point those out to you. The first thing is, when you're looking at, you'll note the length of the vertical curve. And this is the horizontal length of the vertical curve, is 800 feet. Okay, that's eight stations. And typically we'll work with, we won't substitute 800 in our equations, we'll use 8 because we think of things in terms of surveying in 100-foot increments just to keep our numbers down, is something that we can work with. Our approach grade is a plus 2%. Our departure grade is a minus 3%. And what would be A in this particular problem? It's showing as minus 5%. It really should just be a 5% there. Okay. The station for the vertical point of curvature is 800 plus 00. And it's just coincidence that that station is 800 and the length of the curve is 800. Okay. And that's all. That's the only reason that those two numbers are the same, is coincidence. The elevation of the vertical point of curvature is 1,000 feet. Now I'm going to, if you go back, I would like to show you the picture of the vertical curve, just to point out something that's a little bit maybe is unique about this particular problem. What was given to you was the station and the elevation of this point of vertical curvature, PVC, in this particular drawing. What's generally given to in most problems is the station and the elevation of your point of vertical intersection here. So you have to pay attention to what's given to you in order to work back to this. Let me ask a couple of questions about this particular problem that aren't on that sheet. What would be the station of your point of vertical intersection when you look at it there? Well, if you look at that, how would you know where that midpoint is? You know that your curve is 800 feet long. You have equal tangents, so it's going to be 400 feet to get to the PVI. So the station of that point of vertical intersection would be 800 plus 00, and then if it's 400 feet long, that would be 4 plus 00, or the station would be 804 plus 00. What would be the elevation of the point of vertical intersection? Okay, and that's not given to you on that sheet. The way that you would have to work that is that you know that at the PVC your elevation is 1,000 feet, and you're on an upgrade of 2% rise for every 100 feet of horizontal run. It's 400 feet distance, so that would be 8 feet higher at the PVI than the PVC, so your elevation would be 1,008 feet at the point of vertical intersection. So
just grade times the distance.
Grade times the distance would be the way that you would have to work that problem. If you were given the elevation of the PVI and wanted to work backwards to your point of vertical curvature, it'd be grade times distance, but you would be subtracting from that elevation there. Okay. So pay attention to what you're given on a particular problem, and what you would really like to work with is an elevation and a station for your point of vertical curvature. It's given to you in this problem, but they're not always so nice to you. It's more common maybe to get the elevation and station of your point of vertical intersection. You can work with it though if you just pay attention to the numbers here. The other thing about it I mentioned was that the station of the PVI would be 804 plus 00. So when you look at these things down here, you'll notice that at the bottom of the example problem that I'm giving you there, at the bottom of the example problem, you'll see these different stations. You'll notice they go from 800 up to 808. That's the 800 feet length of the curve. X is the horizontal distance from the point of vertical curvature to that particular point on the curve. Notice the first one is 0 because 800 is where the curve starts. 801 is one station horizontal distance from the PVC, and all the way up to 808, which is 8 stations away. And this particular formulation, they're working in stations. The next column in this particular problem says the grade 1 times the horizontal distance. So when we go one station or 100 feet from the start of the curve along that grade line, we have our grade times the length is a 2 foot higher at that point along the tangent. At 200 feet from the start of the curve, we're 4 feet higher than what we started, and right on down the line. Now, again, let me just make a drawing here on this particular picture, because I think here's a place that people get confused. We have two grades, G1 and G2, that we're looking at there, but this series of calculations is calculating elevations at different points along that G1 line, because that's what we're going to be computing is offsets from the G1 line in this particular problem. Okay. The next column there is titled the A times x squared divided by 2L, and that's simply a formulation to come up with y, or the offset between that tangent line that we just calculated elevations for and where the roadway surface is going to be.
That's the drop from the tangent.
That is the drop from the tangent in this particular case. If I draw in the vertical curve, looks like this. What we're computing are these drops from the tangent at each point along that particular curve. Okay. And then if we know what the elevations are, really at the first one it started out at 1,000 feet. At the second one we were at 1,002 feet minus this drop of 0.3. We come up with an elevation of 1,001.69. At the next one we have a drop of 1.25, and that should be from 1,004 feet minus that drop. And we go all the way out to the end where we have a drop of 20 feet, and that would be from an elevation of 1,016 feet at that particular point. So we can compute elevations along those points. And you might notice from this particular formula we could compute the elevation of any point on that curve. If we wanted to compute the elevation at station 802 plus 50, that would be 2.5 stations. Substitute into our formula, we could compute the offset there and compute the elevation for any point along that curve, as long as we knew how far it was from the point of vertical curvature. Now, There are some additional calculations there at the bottom where it calculates the location of the high point on the curve, the station of the high point where it occurs, and what the elevation of that high point is. And just one word of caution, the equations that there's a couple of different ways of working this. This is one way that you can do it. There's another way that's shown in your reference manual. Either one of them is correct, whichever one that you feel more comfortable with. Let me just tell you what the variables are here, because they're not really defined well on this overhead. The location of the high point is shown as x prime on this slide. On your equation sheet previously, it was defined as x sub m. Okay, so we're talking about the same thing here, and this is not the equation that was used on the previous page. So don't try and make it out to be the same. This particular equation is L times G1 divided by this is A in this particular equation. So this equation, if I could, would be L times G1 divided by A, and you come up with 3.2 stations. The station of the high point, remember we started out with at station 800 plus 00, and we came up with the 3.2 stations from the vertical point of curvature, so that comes the station at 803 plus 20, or 320 feet into that curve, not the midpoint. The elevation of the high point of that curve, we started out with an elevation of 1,000 feet. We're on a 2% upgrade, and we're going 320 feet, or 3.2 100-foot increments in this particular case. So the highest point on that particular curve would be an elevation of 1,003.2 feet. So we'd work through that.
You're about at a break point?
Yes.
All right.
Okay, for your algebraic distance, if it's 2% and 2%, 3%, it comes out the absolute number, and it's in the percentage. So 2% and 3% become 5, not 0.05, right?
That is correct. If it's a 2% and a 3%, A is 5. Okay, it's not 0.05.
Okay, if y'all want about a 5-minute break, and we'll